Hey, I just wanted to help out with some of the organic problems that we've been having. So I decided I'd go through a couple of reactions, and we first will look at the solvent that we're using and decide whether it's a weak base or a strong base, or a weak nucleophile or a strong nucleophile, and then decide where the reaction will carry on after that and look at a mechanism. So here, what we've got is 1, 2, 3, 4, 5. So we're going to have 2-chloropentane, and we've got formic acid here, and we're going to be looking at what's going to happen here. So first of all, what we've got here is a weak base, a weak nucleophile. It's not charged, which means that it's not going to have a real strong desire as a nucleophile, but we do have some lone pairs here, which means we can form some bonds. So since it's a weak base and a weak nucleophile, we are going to assume that it carries through with an SN1 or an E1 reaction. What that means is that it's substitution nucleophilic unimolecular or elimination unimolecular. And what unimolecular means is that the rate depends on one thing only, and that is our main reactant here, which is the 2-chloropentane. Now what's going to happen is the 2-chloropentane, since the rate only depends on that, we have to assume that it forms a carbocation. And the way it's going to do that is by I'm just going to have this right here. Now what forms this carbocation is the electrons move to this chlorine here. Okay, so now we have this carbocation. We can go two routes. We've got the SN1 and the E1. Now, we'll start with the SN1. The SN1, what's going to happen is we've got this. See that or any big basket? We've got this the formic acid, and it's actually going to attack this electrophile here. So then, what we're left with and then an H off that, and then off that, COH. Now, if you take a look at the formal charges here, this oxygen is going to have a plus. So to get rid of this plus, what we can actually do is use more of this base here, and actually pull off this hydrogen and then donate these electrons back to this oxygen, so that what we're left with completely is just an O, CH, well. So there's one of our products, and now the next one, we're going to take this carbocation, and this is going to be the elimination process for this one. Okay, and what we've got to remember is that for elimination, what's going to happen is the base is going to come and deprotonate an adjacent carbon. So either this carbon or this carbon. So for this one, we've got a couple hydrogens hanging off there. And on this one, we actually have three hydrogens here. So we've got this acid here. Well, it's formic acid. It's a weak base, obviously. That's just chilling out here with. Yes. just chilling here with its two lone pairs, and it's like trying to decide which hydrogen it wants to pluck off. We could pluck off this hydrogen here, and form an alkene. Those are terrible, sorry. Form an alkene that looks like that. Or it could take this hydrogen, or that one, doesn't matter, and this bond can come here, and it can form that product. Well, we know that according to Zaitsev's rule, the most stable alkene will be formed. And the most stable alkene is going to be the alkene that is formed between the two carbons that are the most substituted. So this carbon is a primary, and this carbon is a secondary. This carbon is obviously still secondary. This carbon is secondary as well. What this means is that this product will not be formed. But what we're going to see is this one. So, for this reaction, we look at it and we see that we've got a weak base and a weak nucleophile. That means our E1 and our SN1 are going to be competing. We then know that it's going to form a carbocation, and that our base is either going to deprotonate our carbocation or it's going to attack it. And I guess I should have pointed out that this carbocation will not rearrange because there's not a more stable conformation for this. If we had a primary, a tertiary carbon here, it would perform a hydride shift. That way the plus could be there. But since we don't have this, we will not see any rearrangement. So don't get confused there. But then our nucleophile is going to come in, and it's going to attack the carbocation and form this product here. Had it come in as a base and deprotonated, we would see this alkene here. So I hope that helps.